Just about to start the meeting. Okay, please wait. So, and we have around 238 participants. They registered for the program, and out of that, 95% to 96% are the faculties of various engineering colleges and institutes. And we just so we have every day we had like 2 sessions at the evening from 6 to 9, and today we have started from 2 p.m. So today we had the first session from of Dr. Shailesh Agarwal sir, who is the executive director of BMTPC. Then just now, just before your session, it was the Hemant Kaushik sir gave one lecture, who is the professor, BIS chair professor at IIT Guwahati. Okay, just now he finished. If you allow, then we can start your session.
Yes, sir, we can start. Not a problem.
Yeah, just 1 minute.
Yeah, hi Aniket.
Hello, sir.
Hello,
sir. Good to see you.
Yeah, thank you for accepting our invitation.
Okay, sir.
So, dear participants, welcome to session 13 of day 6. So, we are delighted to welcome Dr. Aniket Desai. He is the assistant professor in the Department of Civil Engineering at our institute at NIT Calicut. So, he specializes in earthquake engineering with research interest including site characterization, subsurface imaging using active and passive surface wave methods, seismic site response analysis, local site effects, and many more. So prior to joining NIT Calicut, he did his BTech in civil engineering from SBNIT Surat, Masters in earthquake engineering in 2015, and PhD in 2023. Both are from IIT Roorkee. So sir is a young researcher and published more than 19 papers with over 50 citations. He is a member of Indian Geotechnical Society and actively contributes to teaching and research in the field of earthquake engineering. So he joined NIT Calicut as an assistant professor, and also he is a member of our center, that is the Center for Climate Resilience and Disaster Management. So we are pleased to welcome sir and would like to appreciate your valuable time. Thank you for accepting our invitation. Over to you, sir.
Thank you, sir.
Yeah. Please share your screen so that I can see everything is fine.
Yes, sir. Just a minute.
Yes.
Is it visible?
Yes, it is visible. You made full screen, right, sir?
Yes, sir.
Okay.
Just a minute. What happened? Okay.
Yeah.
Okay, now it's full screen visible, right?
Yes, it is visible. Please go ahead. Thank you.
Okay, sir. Again, thank you for the nice introduction. So, my topic that I'm going to talk about today is the MASW method. The full form of MASW is multi-channel analysis of surface waves. So you can get a little idea in the image itself. On the left side, there is an indication of application of a load on the soil surface. So we are applying the load either by hammer or drop load, and then we are generating waves. On the other side, on the right side, you can see that on the soil surface, we have kept different sensors, which we call geophones or channels. So we record the waves in these channels, and then we do the processing, and then we obtain the shear wave velocity profile of soil. So in that way, this method is called multi-channel analysis of surface waves. So I will talk about what are the fundamentals of this method, then some typical applications I will show, and then I will show some uncertainties which are associated with this method. So this is the outline of what I am going to talk. So first I will talk about what is the motivation behind using this method. Then I'll talk about some introductory portion about this method. And then I will explain the basic fundamental concept about this method. Then I'll show some applications of the method. and then I will talk about what are the different uncertainties which are associated with the method. And finally, a kind of concluding remarks in which I will show what are the guidelines or rules to be followed when we are using this method. So first, coming to the motivation behind the method. So a very well-known phenomenon with the geotechnical earthquake engineer is called local site effects. This was predominantly demonstrated in 1985 when an earthquake occurred in Michoacan, Mexico. And after this earthquake, people started giving more importance to the geotechnical aspects of earthquake engineering. So what happened is Mexico City, which is around 400 kilometers away from the epicenter of the earthquake, suffered significant damage. There were so many big structures which got damaged. However, one important observation was even in Mexico City, the damage was concentrated in some particular areas. On the other hand, in the same city, there were areas where negligible damage was observed. So it was found that all the structures which got damaged were located in one particular region which was having soft soil deposits. So soft soil means the stiffness or shear wave velocity would be very less, and that region experienced significant damage. On the other hand, there was another region which was very nearby but having rocky strata. Those regions suffered negligible or minor damage. For example, this UNAM. Okay, so this phenomenon gave rise to the knowledge that at any area, the earthquake waves may travel thousands of kilometers or may travel in any direction, but the top few meters below the soil surface plays a major role in the amplification of the earthquake motion, and therefore the knowledge of the top few meters of the soil surface is extremely important. So why this MASW testing is important? So as we saw in the previous slide, it is very important to have the knowledge of the soil characteristics, and for that very important parameter is shear wave velocity profile, and for that the most common method is MASW test currently, although it was developed in 1999, but after that it has gained lot of prominence. Once you get the shear wave velocity profile, there are numerous things which you can obtain. First is the site classification, then seismic site response, how will soil behave. Then for any area you can do seismic microzonation. Even seismic hazard analysis can be done. Even for liquefaction analysis, the shear wave velocity profile is an important parameter. So with all this, the importance of MASW test has increased in the recent years. So although this would be known to everyone, but just for just recap, I'm just showing what is shear wave velocity. So it is related with the shear modulus of soil, and on the right hand side is a typical shear wave velocity profile shown. It is obtained in a stepped shape from the MSW method. So it shows with how much the depth the shear wave velocity is varying. Okay, so what are the common tests available to obtain the shear wave velocity profile? So initially, conventionally, these geotechnical tests were preferred, which includes the all known tests: standard penetration test, cone penetration test, dilatometer and pressure meter test. However, they have some limitations. For example, from standard penetration test, we obtain the n value, and to get the shear wave velocity, we need to use correlation between n and Vs. Now there are so many correlations available. If you use different correlations, the Vs value obtained will be different. Okay. Another thing is NVS correlation would be applicable to some particular region. Okay. For example, somebody has developed NVS correlation for Calicut, so that will be applicable to this region only. Okay. So that is why when this test, geophysical test came, the use of geophysical test started gaining importance. So the first test developed was spectral analysis of surface waves. In this, only two geophones were used to record the waves, but it had its own limitations. So then multi-channel analysis of surface waves were developed, which contains multiple geophones, and its processing is even better than SESDRRBI test. So it is the topic of my research till now. Then there are some other methods also available: cross hole, uphole, downhole, seismic cone tests. So these are all geophysical tests, and they are having advantage in all three aspects: time, effort, money. The time consumption is less compared to the conventional test. Effort required is less because labor is not required. All the geophysical tests are non-invasive tests. You do not need to drill borehole. You do not need to bring out the soil sample. You can just put it on the surface and get the results. And the finally money, this test consume less amount of money compared to the conventional tests. Okay, now let me show what is the concept behind this test. So you can see that this is a soil profile in which there are three soil layers are shown, and on this side we have kept an impact source. So what we'll do is we will drop the load, we will generate waves, so the waves will travel. Okay, and when the waves travel, on the right hand side we have kept our geophones. So the geophones will record the waves. Okay, and an important thing which you may have observed here is, I will show it again, that the waves are generated. Some waves are getting restricted in the top layer itself. On the other hand, there are some layers will travel up to the deeper depths. So why this? The phenomenon is that the waves of different frequencies are generated. So waves of different frequency will travel at different velocity and penetrate up to different depths. So this phenomenon is called dispersion of waves. So this is the basic phenomenon which is used in the surface wave testing. Okay, now let us see how the methods evolved. So initially the first test that was developed was 1958 steady state vibration test. This has become obsolete now. Later in 1983 the SESDRRBI test came. Then in 1999 the main test which I have worked upon, MASW test, which it was developed. Then recently in 2018 some guidelines have been proposed to use this test. Actually, even when this test was developed, it has its own limitations. People were not aware about the rules to be followed. So in 2018, a proper set of guidelines were developed. And finally, an article showing the complete state of review on MSW test was published in 2023. So this is how the evolution has gone for the surface wave methods. Okay, now let us see how the field testing occurs. So on the left hand, it can be seen that on the soil surface there is an array of geophones. All has to be kept in an array, and all are having same distance between each two pair of geophones. This is the setup which is used to generate waves. Okay, it can be generated using hammer or using some kind of alternate arrangement. So this is an arrangement to generate waves. Once we generate waves, they are recorded in this kind of laptop, and then in this we do the processing. Okay, so this is about field setup. Overall there are three steps. First step is, as I said, the field testing, in which we get the waveforms at different geophones. In the second step, we do the processing of these waveforms and obtain a curve between velocity and frequency. So as I have said, the waves of different frequency travel at different velocity. So that distribution is shown in this graph. Once we obtain this, there is step 3, which is called inversion process, in which we apply inversion to this dispersion curve, and then we obtain the shear wave velocity profile of soil. So these are the 3 steps of the test. Now I will show some typical records which we have obtained. So this is a record obtained after applying one shot. So you can see that from the beginning to end there are 24 geophones. So the first line shows the waves recorded on the first geophone, and similarly for other geophones it is shown. So you can see that initially the wave comes to the first geophone, which is the closest to the hammer. Okay, then obviously it will go to the second, third, and then in order it will go one by one. So this is how the waves are coming. Now when we do the processing of this using different methods, we can create such type of image. This is called dispersion image. In this image there are some particular regions which are showing concentration of energy. So when we extract that data where the energy is concentrated and get those points. So these points are showing the dispersion curve. Okay, so this is the dispersion curve obtained from the field data. Now, coming to how MSW has gained importance. So this graph shows the number of articles per year starting from when the MSW test was developed. So from the beginning, the number of articles have increased. Okay, and on the right hand side, the cumulative number of articles are shown. So with each year, we can see that the number of publications are increasing. These are the areas or disciplines in which the MSW test is used. Although it can be used in so many disciplines, there are various applications, but mainly it is used for earthquake engineering applications, or there are some other civil engineering applications also. For example, transportation engineering, environmental engineering, even water resources engineering. Okay, so in that way, this method is applicable to so many disciplines. Now, how it is used in earthquake engineering? Mainly, sometimes where some area is very much earthquake prone and some construction activity is required, especially when the structure is of very importance. For example, dam or bridge. People do this test to get an idea of what will be the earthquake motion after the amplification if some earthquake is expected. Okay, so that is the main use. And then there are even sometimes after earthquakes on a reconnaissance project, MSW test is used. Recently, when 2023 Turkey earthquake occurred, that area itself was earthquake prone, that was known. So people had done MSW test before the earthquake also. And then after earthquake also, in reconnaissance program, they did the MSW test and got the shear wave velocity profile. Now, there are some other applications which I will show. So this is related to transportation engineering. So the task is to design of a pavement. So even before designing pavement, the knowledge of soil properties is necessary. Sometimes even after designing the pavement, after all the construction also, shear wave velocity profile is necessary. So for that, these people have obtained the shear wave velocity profile. And one important thing that they observed here is the shear wave velocity profile is showing very low shear wave velocity. It is a soft soil. On the other hand, this shear wave velocity of pavement is extremely high. Okay, so according to that, the soil will behave if any earthquake is coming in this particular region. Okay, fine. This is another application related to a railway track. So in railways, whenever train is coming, some vibrations are generated. Sometimes that may also be causing some harm to the soil. So for that, an estimation of shear wave velocity of profile is necessary. So in this study, they have obtained the shear wave velocity profile at the top few meters of the soil. This is another additional or some separate application in which they have obtained a two-dimensional shear wave velocity profile. So what they have done is they have done the MSW test at the region at multiple points, and then some interpolation is done, and then they obtain the 2D VS profile. Such type of VS profile can be used in many civil engineering projects. For example, let us say some construction of some building is going to be done and soil investigation is required. Now people have to decide what should be the number of standard penetration tests are to be done. Many times people are not knowing, so they roughly give the number, and then that may create problems. Sometimes the number of SPT are very less, which will not give the actual idea of the soil. Sometimes the number of SPT done is too high, which will become uneconomical. So what can be done is, initially in that area, a 2D VS profile of the soil can be obtained using the MSW method, which will give a preliminary idea of the heterogeneity of the soil. Suppose the soil is mostly homogeneous, maybe 3-4 standard penetration test can be enough. On the other hand, if the soil is very much heterogeneous, more number of standard penetration tests would be required. Okay, so this is how the MSW test can be used for any civil engineering project. This is another application at some road in USA. So at this place, they have obtained the 2D shear wave velocity profile. Okay, this is an application related to the ground improvement or ground treatment. So many times before any construction activity, it is found that the soil is actually not having the adequate property to do any construction. And so people apply some ground improvement method to improve the soil properties. Now MSW test can be used to make an assessment of what is the improvement in soil properties after applying the ground treatment method. So this first photo shows the site photo of one site, and then this picture shows the initial shear wave velocity profile before applying any soil treatment, and this shows the VS profile after applying the treatment. So if you can observe here ignoring this initial temporary working platform, if you can see here, majority of the portion is having this blue color, that is shear wave velocity may be ranging near to 100 only. Okay, on the other hand, after treatment this color is getting changed, which is coming mostly in the second region near to 200. So in majority of the region the shear wave velocity has increased, that means soil stiffness has increased. Okay, and then finally this third one shows the difference between this and this. So what is the increase in shear wave velocity after applying the ground treatment? Okay, so in this way we can make an assessment what is the improvement in soil property after applying the ground treatment. Okay, now we have discussed the applications. However, there are some uncertainties present in the MSW testing. So mainly they are divided into three types. First is model based uncertainty. So the basic assumption of the MSW test is we assume that only Rayleigh waves are generated when we apply the hammer. Okay, although it is a fact that maximum energy generated is of Rayleigh waves, but some amount of body waves are actually generated during the test, which we cannot ignore. Okay, now those body waves actually get mixed with the Rayleigh waves and they hinder the results which we obtain. So that generates uncertainty. So that is called model based uncertainty. Second type is data measurement uncertainty. So this is related to noise. Whenever we apply hammer load, obviously there is some noise present at the site, which may be due to the passing vehicles, which may be due to the earth's vibrations, or maybe some nearby water body like a river or sea, anything. Okay, so that again hinder the waves generated by our hammer. Third type is inversion uncertainty. So in this, what happens is when we obtain a single dispersion curve and when we do inversion, we can get multiple shear wave velocity profiles, which all would be equivalent to one single dispersion curves. Okay, and the VS profile may be thousands. So which one is correct? We cannot actually directly tell. So this is an uncertainty which is called inversion uncertainty. Now let me give an idea about what are the uncertainties. So let us say this is a dispersion curve which we have obtained from our field testing. And when we do the inversion in the right hand side, we can see that there are so many shear wave velocity profiles are obtained. Okay, starting from this gray color, which are having low misfit value, that means showing better match to the actual dispersion curve, and then there are other profiles also in red color which are having some higher misfit value, but still they are equivalent to this dispersion curve. Then second type of uncertainty is data measurement uncertainty. So what happens here, at the same place, if we apply hammer multiple times and take multiple shots and generate multiple dispersion curves, the dispersion curve will not be same. We will get multiple dispersion curves which are different from each other. So which one should we take? So that creates another uncertainty. Okay, so that's why it is suggested that rather than taking one single dispersion curve, a mean dispersion curve along with its standard deviation should be taken, so that we can account for the data measurement uncertainty. Okay, In that also, one specific method is there. Suppose we have initially some initial dispersion curve and its standard deviation. What we can do is, within this bound, we can generate a random dispersion curve like this shown here. Okay, then we can do the inversion and get its theoretical dispersion curve, which is obtained after generating the shear wave velocity profile. This we can do multiple times. Within this range, we can generate 100 or 200 dispersion curves. For each dispersion curve, we will do the inversion and get the theoretical dispersion curve. So we will get a multiple inverted dispersion curves, and for them we get a mean and standard deviation, and that should actually be matching with the initial mean plus or minus standard deviation curve. When we get such type of things, then we can say that we can actually account for the data measurement uncertainty. Next is the third type of uncertainty, which is called model based uncertainty. So as I said, this is generated because of the presence of body waves. So what happens is, when we generate waves, both the waves are generated, and body waves are although with surface waves. What happens is, with distance, body waves and surface wave get separated. Okay, because body wave attenuate very quickly compared to the surface waves. However, whenever the distance is small, whenever the hammer is very close to the geophone, in that particular setup, this uncertainty can hinder your result very much. Okay, so this is called the model based uncertainty. This is also called near field effects, because this is shown mainly in the near region of the your hammer shot area. Okay, so with all these uncertainties, the whatever results we are obtaining from the MASW test would be definitely containing some kind of uncertainties. So for that, what are the guidelines we should follow to avoid all these uncertainties? So some guidelines have been proposed, so which I want to just mention. So the first guideline is that the distance between the hammer source and the first geophone should be kept approximately 5 to 20 meter. Okay, so we should not keep any distance less than this, and as far as possible we should keep as much as possible. Okay, but whenever some specific source such as vibrosis, in which very systematical waves are generated, in that case source offset can be kept higher. Then second rule comes about the spacing of geophones. So wherever there is array of geophones, we have to specify the inter-geophone distance. So that is specified as 1 to 4 meter. It should not be kept higher than this, because that will again decrease the resolution of your final dispersion image. Then the next is, the length of geophone array should be kept approximately 23 to 96 meter. Okay, so this array length is related to how much depth of investigation you can obtain. Generally, suppose your length of array is 96 meter. In that case, you can get the shear wave velocity profile up to 96 by 2, that is 48 meter. Okay, so your array length decides how much VS profile depth can be obtained. So generally we have 24 geophones, and if we keep 2 meter spacing, so 24 into 2, around 48 meter will be your array length, and then so 24 meter depth VS profile can be obtained. Okay, next is regarding number of geophones, that should be 24 or 48. Okay, generally this is the standard number, and if fewer geophones are used, the test should be repeated with different inter geophone spacing to get the good resolution. Then another important parameter is sampling frequency. Okay, this will again determine how much is accurate is your result. So the standard value suggested is 500 to 2000 hertz. Okay, this is generally followed in all the software which are using MASW test. Then it's about recording time and pre-trigger time, which are suggested as 2 seconds and 0.1 to 0.2 seconds. if you keep this time more than 2 seconds, the problem is that it will also record the unnecessary noise. Many times people keep 3 or 4 seconds. So in that case, we have observed in field that too much noise is coming, and that is, decreasing the quality of your results. So 2 seconds is generally suggested. And then 0.1 to 0.2 second, that is pre-triggering time. So just before the shot, some seconds are required to avoid the leakage. Okay, so this is the general suggested. Then that is about the quality of geophones. So generally the natural frequency of geophones should be 4.5 hertz, which we used in our testing. If you need the data of higher depth, maybe greater than 30 or 40 meter, if you need the data, then the geophone of lower natural frequency should be used, because low frequency is associated with higher investigation depth. So at our laboratory, when I was doing PhD, we had one setup which was having natural frequency of 2 hertz geophones. Okay, so that we used when we wanted to get the higher depth data. Then coming to the mass of the sledgehammer, which should be at least 5 kg. But then if you have a heavier sledgehammer, it has the capacity to give the VS profile up to higher depths. Okay, then this is about how many shots should be taken. One problem is that if you take only one shot, it would be containing noise. On the other hand, you take 5 shots and then club them, combine them, stack them. In that case, you can remove the effect of noise, or at least you can minimize the effect of noise. So it is suggested that at one site or one place itself, you take at least 5 to 20 shots. Okay. Then it is suggested to take forward and reverse shot also. Okay. Because at some place there may be some lateral heterogeneity. To avoid that, we should take a shot from forward and reverse. That means suppose your array is kept, you need to take the shot from the left end also, and after finishing you take one shot from the right side also. And then one more is, if any a priori information from other test is used, for example you have any data of some any other test, CPT or SPT, so in that case you can combine the results of MASW and SPT. Okay, in the processing of MASW you need to select the layer thickness, layer numbers. So if you have any additional detail about that, it will be useful to get better results. Then finally, the dispersion curve obtained from the MSW testing should be further analyzed along with the HVSR curves. So there is another method called horizontal to vertical spectral ratio, which gives the information about the fundamental frequency of soil, which is also an important parameter in earthquake engineering. So if you are having the information about the fundamental frequency of soil, then you can use it to get a better result from the MSW testing. Okay, so overall these are the guidelines. So these are guidelines are mentioned in this article, which is a book chapter which is published by us in 2022. And let us me go through the summary. So MSW is currently the most popular method to estimate the VS profile. Then there are so many applications of MSW in earthquake engineering and in other field also. However, despite so much popularity, it contains its own uncertainties, which must be handled carefully. Otherwise, when your results are erroneous, the error will be propagated in further analysis. So these are some of our publications. Okay, so thank you for listening.
Thank you, sir. Thank you, sir, for the wonderful session. Am I audible?
Yes, sir. Yes, sir. No.
Yeah. Thank you.
Thank you, sir. Thank you.
Sir, drop the cost to test.
Sir, your voice is not coming properly.
Robin sir dropped in the chat box.
Okay.
What is the cost of MSW test compared to SPT?
Okay. So, see, the equipment cost will be, I mean, wherever we got, it was around 10 lakhs. However, it may range between different companies from we are buying. Okay. However, when you go to the testing, the cost of testing is very less compared to SPT. When we did SPT test for one single test, they took around 50-60,000. But for MSW test, for one test you want to go to the field, it may be ranging from around 7 to 10,000 typically.
Okay. Thank you. And if you have get any queries from the participant, definitely I will forward it to you, and they can get the reply from your side. Thank you. Acha, one of the thing I want to like to say, like as I mentioned here, that many of the participants are the faculties of the engineering colleges and institutes. So could you please just they also want to do some research and all those. Could you please like discuss what are the areas that can be explored by them, and they can get a new research area? I think it would be very helpful for our participants.
New research area using this MSW method. That's what you are
Yeah,
asking.
yeah. If
Okay.
someone wants to do new work or something, because all of the faculties that they need to do the research and all those, if you can lighten like few things which they can explore by themselves. Yeah.
Okay, one thing which I have seen in our country is, although MSW is testing is available for at our institute, NITs and IITs, but for field applications, for any construction project, MSW is not used much. So what I suggest, as I mentioned in the talk, is for any construction project, before doing SPT, MSW can be used to get a preliminary idea of what is the soil heterogeneity. Okay, that is one application. Apart from that, whenever we are doing the MSW test, there are three types of uncertainty that I have mentioned. How to overcome that uncertainties, that is one topic of research. And
Yeah.
there are currently many people working on that. Okay.
Okay. Okay, sir. Thank you for the accepting our invitation, and very informative sessions it was. And thank you for sparing your time. Now, would like to, sir, present a small token of thanks from our side. Please accept it, sir.
Thank you, sir. Thank you, sir.
Yeah, thank you, Aniket.
Thank you, sir.
Yeah. Sir, you may leave the meeting so you can start the next session.